Okay, so today I'll kind of talk about the Hamming model of errors, or the adversarial model of errors, where we're trying to transmit some encoded message, and it can be corrupted in any positions whatsoever. The errors can depend on the previous errors, can be arbitrarily complicated, which is what we call the Hamming model. But I mean, we have to put some assumptions, otherwise the error can completely destroy whatever we are trying to send, and there is no hope of communicating anything. So here we can make an assumption about the maximum number of positions which can be corrupted, which I'm going to call T. But other than that, it's arbitrary. And these positions can be wherever the adversary wants them to be. They can depend on our encoded message in an arbitrary way. And so we are not going to make any assumptions. And this is useful as an abstraction in computer science in particular, because a lot of the times we want to think of our algorithm as trying to communicate something, and these errors are some sort of problems that happen either with the data or with the kind of maybe the algorithm is reading some sort of auxiliary information like randomness. And we'd like to give worst case guarantees that no matter what happens to the input of this algorithm, if it doesn't kind of happen in too many places, our algorithm will run correctly. And this is the kind of thing this Hamming model captures. So perhaps not so surprisingly, it's quite useful in the worst case analysis of algorithms or related questions in complexity theory. Just a reminder of this model. So the message is still going to be kind of encoded into, let's say, some block or sort of n symbols. And we are going to think of the encoded message as n symbols, each between, let's say, 0 to q minus 1, which is also called the finite field. I'll get to more details of this field in a minute. But this is this q is also called the alphabet size, or this fq is called the alphabet of the code. Here we are going to think of the message space also as in the same space q, although in general it doesn't have to be, but if it's a different field, we can always embed it into this one and so on. So it'll be convenient to work with the case where both messages and the encoded or the code words are both, each symbol still belongs to the FQ. The number of symbols is different, which is the redundancy or which will govern the rate. Okay. And let's say what comes out is also n strings in Q, but this is corrupted now. So it's corrupted in up to T positions. And as we kind of also did partially last time, we will kind of think of two ways of thinking about this code. So we can think of C as a subset of all possible strings that we can send. Can be a subset. If you are going to think of a linear code, it will be a subspace and so on. The other way to think about it is an encoding function. So and we will also denote this by the same letter C. So we can either think of C as kind of mapping messages to code words, or just as a collection of code words of the right size. And as we saw in the case of linear codes, kind of mapping messages to code words is very cheap. It's just some matrix multiplication. So it won't really concern us too much, and we can switch back and forth between these two views. Most of the time, we'll actually think of C as just a subset of all possible strings that we can send. So just the code book will be the view we will take. But either of these is fine. You can just think of it as the image of the encoding map or the subset of strings. Okay. Any questions about this before we proceed? All right. So just like in case of the Shannon model, the governing quantity was the capacity of a channel, and we were trying to understand how to design codes that match the capacity of the channel. Here, the channel is kind of just terrible. Like the only thing that we know about the channel is that it will corrupt at most some t positions. Okay. And so the quantity of interest which will kind of govern, or which we will need to understand, is what's called the distance of a code, which is just if you look at two code words, in how many positions do they differ. So formally, we will consider the Hamming distance between strings over a finite alphabet. And the Hamming distance just denotes the number of positions in which they differ. So this is a number between 0 and n, an integer. And it's a metric in the sense that you can check that the distance between, so it's first of all, it's symmetric by definition, and you can check that the distance between x and z is at most the distance between x, y plus the distance between y, z, just the triangle inequality. Okay. And in particular, you can check this for the Hamming distance. Okay. And for a code, we just define the distance of a code as the minimum distance between any two code words, or any two. So here I'm thinking of C as a set, as it says, and you can think of the distance between any two code words, or the minimum distance between any two code words as the distance of the code. Okay. And should have said this earlier, but we are going to, at least in this lecture, we'll think of Q as a prime number. We can also think of prime powers, but just sort of, it's a slightly more complicated setup to define arithmetic there. And FQ denotes the field modulo Q, which means that addition and multiplication are done modulo Q. And I'll remind you of some of the properties of this structure that we will need. But just to, for now, just think of Q as a prime number. Any questions about the setup or the distance of a code? Okay. Now, as I said, the governing quantity is the distance of the code. So in particular, a code can correct t errors if and only if the distance is a bit larger than 2t, or so yeah, strictly greater than 2t. Yeah. And the proof is mostly in this picture. So suppose we sent x1 and it got corrupted to y. So these balls are kind of drawn in the Hamming distance metric. And we will denote by b x1 comma t as the set, let's call it z, such that the Hamming distance between x1 and z is less than or equal to t. So z is not necessarily a code word, it's just any element in whatever space we are considering. Okay. So basically all corruptions that sort of all possible strings that we can get by corrupting x1 in at most t places. And so what we would, by saying that we can correct t errors, what I mean is that if I sort of was trying to send x1, no matter what you receive inside this green ball, you should output x1. And that's, so your code should be able to distinguish this x1 from any other x2. So in particular, this means that if I look at this green ball and the red ball, or whatever string you can get potentially by a corruption of x1 versus all strings you can get potentially by a corruption of x2, they should be separate. So when you get to a y by a potential corruption of one of the code words, there is no doubt where it came from. And this in particular means that the distance between x1 and x2 should be greater than 2t. Otherwise, there will be a point. So the same argument goes in both directions, and you can prove if and only if, although I'm not giving the complete proof, I'm just sketching it. And this is true for all x1, x2 in the code. So in particular, it means that the distance of the code must be greater than 2t, so greater than equal to 2t plus 1. Okay. Any questions for this proof? It's just a sanity check, sort of saying that the notion of the distance is the right thing to study if you are in the Hamming model. Okay. And just like we studied the notion of what is the best rate we can achieve if we are trying to correct errors for a particular channel with high probability, in here, the quantity to study is, or the trade-off to study is a trade-off between the rate of the code and the distance of the code. And here we are just going to think of because the message space was f2 to the fq to the k, and the encoding is fq to the n. So we're just going to think of the redundancy, measure of redundancy as k over n. So so rate distance trade-off is just studying the relationship between k, n, and the distance of the code. Although the picture is not quite as clean as what is known in the case of, well, I guess it's not completely clean in the Shannon model either. It has a name. So there is the notion of Shannon capacity, and we know that we can always achieve Shannon capacity, but it's not completely specified in the sense that we still have to compute the capacity of a given channel, and that's not always an easy task. Here, we are looking at kind of rate versus distance, and there are few methods known for showing some sort of trade-offs, although there are different bounds. Some of them work better when q is small, some of them work better when q is large, and some of them work better when sort of the ratio of k versus n is somewhat large versus small, etc. So I'll give two of these bounds, some very basic ones, but there is kind of an entire industry of different sorts of bounds trying to optimize the bounds which work in different regimes, etc. Okay. The first bound is what is called the Hamming bound, and this is just repeating the argument from the previous picture. So if you are going to be able to correct t errors, then we must have that for every code word or for any two code words, let's say, the balls around them of radius t. But again, I'm thinking of t as about half the distance of the code with this floor in case it's odd. Then these should be empty, and so the total number of points is fq to the n. And if I look at every code word and I look at a ball around, and yeah, the other thing to notice is that the size of a ball around any code word of radius t, or sort of the number of strings that I can get from t corruptions, is the same as if I was just corrupting around the center 0. So it doesn't matter which code word I start from. All I need to know is how many positions that I changed. And for every change that I can make, I will get some new element of fq to the n. So it's just the points in the ball can just be described by what positions I changed my starting code word at. So I can, and the number of ways of changing the starting code word is the same no matter where you are or what code word you start from. So for every code word, there is this set of size B0t around it, or this ball around it, which kind of belongs to this code word in the sense it doesn't interact from anything else. And all of these are disjoint sets, and together they live in this space fq to the n. So then we just get the size of the code cannot be too large, and we get a bound in terms of the size of the square. Any questions about this? This is just more or less the same argument as in the previous proof. Okay, so let's do an exercise. Recall that we talked about this code which we called the Hamming code, which was subset of f2 to the 7, or it was in fact a linear code, and we defined it in terms of the parity check matrix as a set of all x such that h times x is equal to 0. And my question is, what is the distance of the code, what is the size of the code, and let's check how it compares to the Hamming bound. Any guesses on what's the distance of the code, or what's the size of the code first? Or if it's you're thinking of it as subspace, then what's the dimension of this subspace?
Four, right?
Sorry, the dimension is 4.
So it's 2 to the 4.
So the size of the code is 16. And what is the distance of the code? Actually, it's a little bit of a trick question. So we proved last time, or we kind of argued last time, that this code can correct at least one error. You make an error in any one position, and we multiply the vector with the error with h, and we just actually get the location, because the columns of this are this kind of numbers 1 to 7 written in binary or something, right? So we know that because it can correct one error, the distance of the code is at least 3. And then you can check that the distance cannot be more than 3 because it's actually tight according to the Hamming bound. So the size of a ball around 0 of radius floor of 3/2 is just ball around 0 of radius 1, and that is just 8, because if you have a 7-bit strings, 7-bit string, there are 8 ways of changing it in less than equal to 1 positions. Okay. Change any one of the, and so we get that the size of the code is less than equal to 2 to the 7 divided by 2 to the 3, which is equal to 2 to the 4. So it's optimal. If the distance was any larger, the size of the code would need to be even smaller, but we know that the code has size 16. So in particular, the distance is exactly 3. You can also prove this in other ways, but here I just wanted to show that it's indeed tight for the Hamming bound. Okay. Any questions about this computation? All right. And it's also interesting to consider the asymptotic form of the Hamming bound. So suppose you can suppose the fraction of errors is delta. So the number or the distance, so the distance is, let's say, delta times n, or rather delta sort of distance divided by n is about delta. Then you will need to compute the size or the number of points in a ball of radius about delta over 2, or the number of code words you can reach by corrupting something in delta over 2 position. And this is something we've already estimated in terms of binary entropy function in one of the very first lectures using subadditivity of entropy, the number of binary strings with delta n ones, or at most delta n ones. And you can check that the rate of the code in this case will be 1 minus the binary entropy function applied at delta over 2. And even for this setting, it's a bit far from what we actually know how to achieve, even using random non-explicit constructions, etc. What we know is how to get the binary entropy of delta, which is as a construction, which is something called the Gilbert-Vershamov bound. But there is a bit of a gap. And I mean, there is a generalization of this to larger alphabets and so on. It's just a question of counting the size of a Hamming ball. But this is just a nice exercise to check the asymptotic form, at least when your alphabet size or Q is 2. Any questions before we proceed? Another bound, which the Hamming bound applies for all fixed alphabets, although it's not always the tightest bound one can get, and there are different bounds which apply in other regimes. In particular, when the alphabet size is very, very large, there is a different bound called the singleton bound which applies, and this is independent of the alphabet size. So not surprisingly, it's quite weak when Q is very small, but we will look at codes, and it's sometimes easier to consider codes when Q is sort of going to infinity, or at least as increasing as a function of n. And so the singleton bound still says something about that case when Q is not necessarily fixed. And yeah, this is due to Richard Singleton, but the proof is not kind of too difficult. It's just, let's say we define this set And I mean, the bound just follows from observing that for an appropriate value of R, this set's CR should be there should be a bijective mapping between the code words in this set CR. So let's do that. Sorry. So, sorry if I'm a little slow today. I'm not feeling that well, so I apologize. But okay. Okay, so maybe okay, maybe I'll leave this as an exercise, but let me say that you can take R to be K plus 2t or roughly K plus 2t. And maybe let me ask you to do this argument that check that these should be sort of non-overlapping sets, or for X, if I, for X1, if I make T corruptions, I should not get something to within T corruptions of X2, which is kind of the argument we had before. Sorry, I'll come back to this later if needed. But let me get to the part which I want to talk about in terms of Reed-Solomon codes, which is how we can actually design codes which can correct up to T errors or can handle kind of worst case errors. And in particular, we will kind of step away a little bit from the techniques in information theory that we have looked at, or the kind of probabilistic analysis, and handle some sort of techniques which can let us handle things in the worst case. And a unifying theme in all of this, so today in the next lecture, is the fact that in some sense, polynomials are a robust object, that you can take a polynomial or some sort of low degree curve and move it in a few places, but then you can't really change it to a different curve, and we'll see different ways of making this precise. And so it's not so surprising that polynomials are kind of very useful in construction of many different kinds of codes. And in particular, we'll be talking about polynomials over finite fields and use a few properties of finite fields. Let me remind you of some of the properties that we will need most often. So as a reminder, this field FQ is the set of numbers 0 to q minus 1 with addition, multiplication, etc. defined modulo q. And we will think of q as a prime number. You can think of q as a prime power, but then you need to define all these operations modulo some other polynomials. So it's a little more involved, and we'll just stick to the prime case just because it's very simple to define everything. A reminder about Fermat's little theorem that for any prime q and a, which is an element of the field, a to the q, or so let's say a is between 0 to q minus 1, then a to the q is equal to a mod q. For 0, it's 0, but for others, a to the q minus 1 is 1 if a is non-zero. So in particular, it means that when we are kind of looking at powers of any number a, it will never make sense to look at powers higher than q, because after that we'll just be repeating things. And so we can define polynomials over this field. So these will just be formal expressions where we are thinking of coefficients coming from elements of this field fq, and multiplied by powers of x. And as we said earlier, we will limit to thinking of powers of x which are less than q. So between 0 and q minus 1. This is the set of all polynomials over a finite field. And we'll also need to consider polynomials of kind of bounded degree, where even if q is very large, we restrict ourselves to talking of polynomials of degree d, which can potentially be smaller. And I'll say polynomials of degree d, what I really mean is degree at most d. So you can have that the largest coefficient is 0. I'm not restricting to saying that the coefficient of x to the d is necessarily non-zero. So this is just degree at most d. And a useful fact which kind of makes this issue precise, that you can't really change polynomials by changing, or a curve by changing it in a few positions, is what's called Lagrange interpolation. Which is that if you have a degree d polynomial, or polynomial of degree at most d, really, and you tell me the value of this polynomial at any d plus 1 positions, then you have told me everything about this polynomial, or I can uniquely identify this polynomial. And in fact, there is even a formula to write down precisely what this polynomial is. And this is the way to compute it. Okay. And I'll give kind of, or sketch a couple of different proofs of this in the next slide. But a useful corollary of this, so notice that here I'm saying a1 to a sort of d plus 1, which are the points at which I'm evaluating the polynomial, need to be distinct. Otherwise, you haven't given me enough data. You just evaluated the polynomial at the same point twice, then it's not as useful. The values need not be distinct. They could be anything. In particular, they could all be 0. And so if you tell me that this polynomial is 0 at d plus 1 points, then if you look at the Lagrange interpolation formula, it will give you something where all these coefficients are 0. And so I'm claiming that 0 is the unique polynomial which satisfies this property, sort of which is 0 everywhere. The contrapositive of this is that if I have a polynomial which is not everywhere 0, then it can achieve the 0 value only at d points, okay? Or at most d points, no more than d. Okay. So more generally, Lagrange interpolation, and in particular this fact, will be quite useful when dealing with polynomials. Any questions about any of these properties before we proceed? Okay, let me sketch a couple of different proofs of Lagrange interpolation, because they're all sort of, they're both useful in their own ways. I'll kind of ask you to complete each of these proofs, but the first proof, which illustrates so even a procedure for finding such a polynomial, but not necessarily a formula, is to realize that a polynomial is described entirely by its coefficient. It's just a question of finding these d plus 1 numbers, C0 to CD. And secondly, even though it looks like we have powers of things and so on, if we just focus on what are we doing in terms of these numbers C0 to CD, we are solving linear equations. These A1, A2, and so on just give us multipliers for the linear equation. And in terms of the numbers C0 to C sub D, we are just solving linear equations, D plus 1 linear equations in D plus 1 variables. Okay. Does that mean we always have a solution? Does that mean we can always find C0 to C sub D? Just a pop quiz in terms of linear equations. I mean, not quite, because there might be dependencies between these linear equations, or the matrix that we are looking at on the left need not be an invertible matrix in general, but you can check that the determinant of this matrix is proportional to it's some sign sort of plus or minus 1 times this. So in particular, this is where the condition that all the AIs are distinct comes in. If all the AIs are distinct, then the determinant is non-zero and the matrix is invertible. And that gives you a way of finding these numbers C sub 0 to C sub D. Doesn't give you, I mean, you can work more on it to find the exact formula that I mentioned on the previous slide. But we don't quite need the exact formula. All we need to know is that there is a unique sort of polynomial or unique solution for numbers C0 to C sub D that we can find if we are given the value of the polynomial at D plus 1 times of its degree at most. And that this proves, although the exact expression is a bit different. Another way of proving this is to check that these polynomials that I wrote down are linearly independent. This polynomial 1 for each I, which is kind of given by looking at all A sub j's except for AI and then multiplying them with some denominators. Linearly independent in the vector space of polynomials. In particular, there are kind of D plus 1 polynomials. And the degree of each polynomial is less than equal to D. As written, it's exactly D. But so, okay. So these form a basis for the D plus 1 dimensional space of polynomials of degree at most D. So whatever polynomial you're trying to find has a unique representation in this basis. And so in particular, the polynomial that you are interested in, which takes values sort of BI at each AI, can be written in terms of this. So that's another way of checking this. And yeah, I'll let you complete both of these proofs. So in particular, I want to sort of emphasize that in the first proof, it shows that finding this polynomial is a question of solving linear equations. And this is something which we will use repeatedly in decoding algorithms for our codes. Any questions about this?
So it seems like proof 1 works for any field. Is that true? We didn't use anything about F sub Q.
Great point. So we used one thing. We used the fact that all the AIs are distinct. So in particular, the size of the field is large enough that there are D plus 1 points. And then it does. And so does the next proof, the linear independence. So both these proofs will work as long as the field is large enough that you can indeed evaluate this polynomial. Right. Any other questions? Sorry if I'm a little slow today. Okay. So now we will use these properties to construct codes, and in particular, we'll construct linear codes, which will have the required properties. So just a reminder on linear codes. Now it's not just a subset of fq to the n, but it's a subspace of this vector space fq to the n. Okay. And as we saw in the Hamming code case, if the dimension of the subspace is k, that also means that the size of this code is q to the k. So we can think of either dimension or the size, they have the same information. And we can represent this code in two different ways in terms of the generator matrix or the parity check matrix. And we saw some properties of these matrices. One significant simplification that we can do, I mean, it's not difficult, but it's useful. In case of linear codes, is that instead of studying the distance, we can study a different quantity, which is distance from zero. So we don't need to consider kind of a quadratic number of pairs, or we don't need to consider all x1, x2, or xy and look at their distances between them. We can just consider all code words and look at their distance from zero. By the way, it's a subspace, so zero is always in the code. And the claim is that it suffices to look at sort of the weight of a code word, which is just the number of non-zero positions or its distance from zero, number of positions in which it differs from zero. And the proof is quite simple. It's just if you want to look at distance between x1 and x2, it's just the size of the set such that ith position of x1 is not equal to the ith position of x2. Which is the same as saying the ith position of x1 minus x2 is not equal to 0, which is equal to the distance of x1 minus x2 from 0. Okay. Where did I use the fact that the code is linear? Or why does this prove what I want to prove?
It's closed, so you can use x1 minus x2.
Sorry?
Obviously, it's a linear space, so it's closed under like addition.
Yeah, exactly. So because it's a subspace, I know that x1 minus x2 is also in the code for all x1, x2, which are in this subspace. So so then I get that the distance of the code is at most the minimum weight of any element in the code, because for every pair, the distance of the code is the minimum over all pairs. For every pair, I could give you a code word such that its weight is the distance between those two code words. And the other direction is also true, because I can only consider pairs involving 0. What I proved right now was actually this. And the other direction is true because for every pair, you can only consider pairs involving 0, and that's an upper bound. Any questions about this part? Okay. A very useful linear code, which is sometimes is used as such, sometimes serves as a kind of a starting point for other constructions, is what is called, or it's really a family of codes called the Reed-Solomon family of codes. And the family of codes in two senses. One, of course, for every n, there is a subset or subspace of fq to the n. So it's a family which gives you different subspaces for different values of n. But even within the same value of n, it's parameterized by something. So fix a value of n, and then we get to pick n different points inside this field fq, which are distinct. And in some sense, the code is parameterized by this set S that we picked, and it's possible that some of the properties we will prove are general; they are true no matter which set S you pick, as long as the points are distinct. But it's possible that some other properties are better for some set than others. So you might, and there are theorems which say that if you try to pick a random set S and define a Reed-Solomon code over that, it has some nice properties, etc. So it's still parameterized by this set S, or the evaluation set. But we will treat it as arbitrary for now. Another thing is, because they need to be distinct, we must have Q which is larger than n. And this brings us to a significant disadvantage of Reed-Solomon codes, that Q needs to be very large for this code. And this is a bit different from the kind of setting we saw in the Shannon model, where we had a fixed finite alphabet and we were sending strings of length n. Here, the size of the alphabet itself depends on n. It's not just that we fix an alphabet or a universe and are sending strings of length n over it. So the way this is usually handled is, you kind of think of this code and then combine it with some other codes to try and reduce this alphabet size q while giving up some other properties, etc. But let's start with this one. And let me describe it according to both our ways of thinking about codes. One is C as a subspace. So in particular, I can think of it as the evaluation tables of all code words. So you can think of a polynomial f and evaluate it at all points, and that gives you a string of n elements of q. And let's say I will restrict myself to polynomials of degree k minus 1. And to prove that it's a subspace, so this is a vector coming from evaluating any polynomial f on these n points. And if I can prove that sort of if f1 evaluated at these points is in C, f2 evaluated at then f1 plus f2 evaluated at these points, or rather C1, some linear combination evaluated at all these points is also a valid code word, then I've proved that it's a subspace. And that just follows from the fact that if f1 and f2 are degree d polynomials, then any linear combination is also a degree d polynomial, and in particular, we're taking d as k minus 1. So this is a subspace, just using the fact that the set of polynomials is a subspace, so their evaluations also form a subspace. The other way to think of it is as a map or an encoding, which is, and there are actually a couple of different ways of thinking about it as a map. I'm describing one. So think of the message as being encoded as the coefficients of a polynomial. So suppose you were given k numbers, and you thought of forming a polynomial out of them of degree at most k minus 1 by just using them as the coefficient of the zeroth power, first power, etc. You get a polynomial, you evaluate it on these n different points, and send that as your code word or as your encode. Okay. So that's a way of encoding it. Another way of thinking about it, which will be useful when we talk of generalizations, is instead of the message as thinking of the message as coefficients, think of the message as the values of this polynomial at k points. Let's say the first k points in the evaluations. It could be some k points, any k distinct points. And we know from Lagrange interpolation that this specifies a unique polynomial, just giving me values at k distinct points. So now for encoding, I will find this polynomial using Lagrange interpolation and then write down its values at A1 to AN and send it to you. Okay. It's the same code because it's always evaluating a polynomial of degree at most k minus 1 at n points. Although you may want to check in each of these cases, which is the generator matrix, or how do you think of it as a linear code. So it's a subspace, and that's easy in each of these. But here you may want to check that this is linear. So that's just another way of thinking about. Any questions about the definition of Reed-Solomon codes? Okay. So let's compute some basic quantities. First, to prove linearity or to find the generator matrix, in the case when I've given you the coefficients of the polynomial, it's easy to check that this is the generator matrix, is pretty much the same as we saw in the Lagrange interpolation case. Okay, so that's the generator matrix in one of the ways of thinking about encoding. And the other way of thinking about encodings, I'll leave you to compute the generator matrix. So in particular, it's useful to realize it's a linear code in different ways. You can also think about what is the parity check matrix. So that's okay. And as we saw before, to understand the distance, we just need to understand the weight of or the number of non-zero entries in any code word, or number of points at which any polynomial evaluates to non-zero. Just because that is equal to the distance of this code. And as we said before, using Lagrange interpolation, that the number of points at which, number of distinct points at which it can be equal to 0 is less than equal to the degree of the polynomial because a degree d polynomial can have at most d roots. Otherwise, it will be the identically 0 polynomial. And yes, I should have said that when we are looking at the distance, we are only looking at non-zero code words. Otherwise, if you're allowed to look at 0, then the weight is always 0 for that. And here, non-zero code words correspond to non-zero polynomials. So as long as the polynomial is not 0 everywhere, it's 0 at most k minus 1 points. And so the number of non-zero evaluations is at least n minus k minus 1. So in particular, the distance is n minus k plus 1, which is tight for what we said in the singleton bound. So it's, in some sense, it's optimal in terms of rate and distance, except remember that we are using this fact that q is at least as large as n, which is a very significant assumption. And a lot of the time we would be interested in designing codes where q is a fixed constant rather than growing with it. But that's not necessarily the case here. The reason this code is nice is that it admits some very nice algorithmic properties. In particular, you can recover from any t errors. T is as large as it can be, and there is even an efficient algorithm to do this. And as we will see in the next lecture, even if you kind of make a larger number of errors, there is a different notion of recovering from these errors, which is to say that maybe you can't find a unique code word or a unique green ball within which things should lie, but you can find a small list of candidates. And we will see in the next lecture that if you're willing to relax this notion of recovery to having a list of potential candidates, a small list, then we can even recover from 99% errors or extremely large number of errors. Okay. So here, if n is much larger than k, then we are kind of recovering from errors in about half the positions. And next lecture, we'll see that with a slightly relaxed notion of recovery, we can even recover from almost all errors in almost all positions. And both these algorithms kind of use this properties of polynomials, and so they are in some sense play on these kind of proofs of Lagrange interpolation that we saw earlier. And even when we are trying to design codes over smaller alphabets, kind of these polynomial intuitions play a sort of important role in many of these constructions. So in some sense, this code is a building block for many of the others. Okay. So let me give you an algorithm for correcting about half the errors, or n minus k over 2, which is the best we can hope for. The distance is n minus k plus 1. So this is about distance over 2 fraction of a number of errors. Let's suppose you tried to send me the evaluation of this polynomial at n different points, so f of a1, f of a2, and so on. There were some errors, some t errors in the transmission, and I received y1 to yn. My first claim is that if I knew the positions where the errors occurred, then the problem is very simple. Okay. So if I know where the errors occurred, then the problem is very simple. Any guesses why?
This is a field.
So,
Are we assuming that you've defined this error locator polynomial?
Well, before we go there, let's say, I mean, so the error locator polynomial is kind of trying to find the positions where the errors occurred. Suppose I just tell you that, or sort of, you sent me a corrupted code word, the adversary kind of corrupted, let's say, the first t positions, but was nice enough to tell me that they corrupted the first t positions. Now I claim that I can very easily, so the error locator polynomial is not necessary now. I'm claiming that I can still solve the problem, and I can just decode. Does the question make sense? Max, is the question clear? Oh, sorry, it was David that was answering. My apologies. Okay. So it again goes back to Lagrange interpolation. So as I said, if I know the value of a degree d polynomial at d plus 1 points, then I know the polynomial. And the degree in this case is less than or equal to k minus 1. So it suffices to know the value of this polynomial at k points. And if you sent me n values but told me that t of them were wrong, I can use the other n minus t. And as long as the other values are larger than k, I can use Lagrange interpolation. Okay? So as long as I have k correct values, I'm in good shape. And so as long as t is less than or equal to n minus k, I'm in good shape. T is actually half of n minus k, at most half. So if you told me where the errors happened, I can actually live with n minus k corruptions. And the interesting part is that even if you don't tell me where the errors happen, I can live with at least half as many corruptions, or I can still correct them, even if I don't know where the errors are. That makes sense? So this is just to set up a baseline. And the entire difficulty in the decoding algorithm is actually figuring out where the errors are. If we knew that, then the problem is very simple. We just use Lagrange interpolation. Or solve a system of linear equations, whichever you find easier to think about. Okay. And the way you kind of capture this is by saying that suppose I don't know where the errors are. Let me try to capture the property of there being an error also by a polynomial. And instead of solving for one polynomial, I will solve for two polynomials. And so for that, let's formally define this, what we call the error locator polynomial, which is supposed to be 0 if and only if f of ai is not equal to yi. So there was an error in this position. Of course, I don't know the positions where the errors happened, and so I don't know the error locator polynomial. This is just a definition of what it needs to satisfy. Okay? That's not to say that I know how to construct this. But then there is a relaxed condition that it should satisfy, which is that for all I, if I look at E of ai times f of ai, then it should be equal to E of ai times yi. Because there are two cases. If f of ai is not equal to yi, then E of ai is equal to 0, and so both sides are 0. And otherwise, it's not. It's non-zero, and it cancels out from both sides. So this condition is always satisfied. Irrespective of whether I know E or not. E must always satisfy this condition. This is not about some AIs, it's satisfied for all AIs. And we will use this as an intuition for our algorithm. We'll basically think of this as one polynomial G, think of this as another polynomial, well, the E polynomial, and we'll just solve for both these polynomials. And we'll see on the next slide how to solve it. And then basically divide G by E, and that will be an answer that will claim that that's the F we are looking for. Okay. We'll need to prove a few things. I should say that this algorithm is due to Welch and Berlekamp. It's kind of mentioned in a US patent in 1986. And the algorithm itself is just, we can make what we just said precise. So we're going to find polynomials G and E with the following properties. So going back to the previous slide, we need E to be 0 at most t points, and its value is completely unconstrained at other points. So we can take the degree of E to be less than or equal to t. If it's less than or equal to t, there are kind of t+1 coefficients, and being 0 at t points is still doable. It's just going back to the system of linear equations. We have one more variable than equations, and we'll see all of that in a second. But here, because we don't know where we should make it 0, that's not the condition we will actually check. The condition we will actually check is that if we think of G in our mind as E times F, then the degree of G should be K minus 1 times plus T, because the degree of F was K minus 1. Those are all our code words. They are degree K minus 1 polynomials. And G is supposed to be E times F. So we'll think of a degree of G as K minus 1 plus T, degree of E as T. And we will require this condition that for all I, G of AI is equal to E of AI times Y. Everyone okay with the conditions we are asking for on the polynomials? We still have to prove that these conditions, I mean, it's kind of clear from previous discussion that if G was indeed E times F, and if E was indeed the error locator polynomial, then these conditions are satisfied. But that's not to say any solution that satisfies these conditions is a good one. But the algorithm is we'll try to find any solution which satisfies this. So output G divided by E, which is just kind of division of univariate polynomials, which I'm not discussing in details except for saying that it can be performed in time polynomial in the size, the field size, and well, I guess the degree of the polynomial. And is there like field size is bigger than n anyway. And how do we find such G and E is again observing that this is again a system of linear equations. We can again think of G and E as specified by their coefficients. And the conditions we wrote down can be just thought of as these linear equations. You can verify that for each Ki, we are evaluating G, which corresponds to this part of the column vector and this part of the row. And we are kind of writing the right-hand side on kind of minus E, which corresponds to this parts. And we are just saying that this linear equation is equal to 0. The number of variables is equal to K plus 2T plus 1, which is kind of 1 plus the sum of degrees of both these polynomials, or like both these polynomials, and number of equations is equal to n. So, and this is a homogeneous system, so has a solution if the, and has even a non-trivial solution. So if it has a number of solutions, as long as the number of equations is less than the number of variables. Okay. I need strictly less than because I need E to be not identically 0. If they are equal, the only solution I will get is equal to 0. So this is okay. And now we need to claim two things to show that the algorithm works. The first is that there exists at least one solution, which is not the identically 0 polynomial, which is not identically 0. And this kind of follows from the discussion of one candidate solution that we have, that let's say I is the set of points, the set of error locations. And then we can always take E to be which is 0 on all the points where there is an error, and for any point which is not an error, the polynomial is non-zero because all the AIs are distinct. And we can always take G to be F times E, where F was the true code word that was set. This is just to say there is some solution. So there exists a non-zero solution. And the other thing we want to claim is that any two solutions give us the same ratio G divided by E, which we know that at least for the intended solution is equal to our code word F. So no matter what solutions we find, the ratio will be equal to our intended code word F. And this follows from the fact that since the E's are non-zero, we can always think that's why we are dividing. But let's look at G1 times E2 at any point AI. This is equal to yi times E1 at the same point AI. This is the definition of, or like this is a condition on G of AI times E2 at the same point AI. But this is an expression which is symmetric in E1 and E2. So this is actually equal to G2 times E1 at AI. So G1 E2 and G2 E1 are polynomials which agree at n points, and you can check that the degrees of these polynomials, is less than equal to the degree of G plus the degree of E, which by our definition of T is less than n. So if these polynomials agree at n points, then they must be the same polynomial, or G1 minus G1 E2 minus G2 E1 must be identically 0, because it's 0 on n polynomials and it's on n points and its degree is less than n. So that tells us that these two polynomials will then agree on all their inputs. So in particular, the ratio of G1 versus E1 and G2 versus E2 will be same for any two solutions that we find. And because we know that at least for one solution, G comma E, the ratio is equal to F, for all solutions, the ratio will be equal to F, which is the code word we were seeking. So that's an algorithm which basically recovers finds the positions where the errors happened and recovers the intended code word without all that it pretty much uses is this property that a degree D polynomial can be 0 at most D points. A few different versions of this statement, and the fact that we can solve linear equations over finite fields is all that is used in the algorithm. Okay? Again, in a few different ways. We'll talk next time about kind of more sophisticated notions of decoding which also apply to these kind of polynomial codes, and we'll in particular consider polynomials in two variables rather than one variable, etc. And this is a property called list decoding, which was defined more recently, but it's also one reason why Reed-Solomon codes actually have been very useful. And then this will be the week when we talk about coding theory. Starting next week, we'll start talking about information theoretic applications and theoretical computer science. So the material from next week onwards will not be on the exam. So the portion that will be in the exam and will be covered in the homeworks will end this week, and then we'll do some hopefully fun applications in the next couple of weeks. Any questions? Sorry, I was a little out of it today, but hopefully not too confusing.